Siri, pick a number between 10 and 20.
It's 11.
It's 11. Jeez. Lightweight. One, two.
That's it. 11. It's a lot harder than it looks. Alright, so today we're looking at section 12-2, which is dealing with arcs and chords. So what do we need to know to solve these different problems with arcs and chords? Well, first let's look at the central angle. Now we're going to take a circle down here, and we have the center of the circle right there. And if we connect the, I can't get it. There we go. So if we get the radius for the circle, I'm going to use both radii, and notice that I create an angle right here. Well, that's the central angle because it's an angle with the vertex at the center of the circle. So this guy right here, that would be my central angle. Now let's go ahead and label different points here. So just say that this point, let's say that is point A, the center B, and point C. So my central angle, I'm going to say that is angle ABC. So get set, the central angle is angle ABC. Now the central angle is going to be, if I take the actual angle measurement, remember I'd say M for the measure of angle ABC, that'd be, let's say, 35 degrees, just throwing a number out there. But that's what the central angle is, it's this angle right there. Well, notice that when I create the central angle using both radii, I also get this portion right here on the circle. Well, that is an arc. An arc is the portion of the circle contained between two endpoints. So point C and point A, those are the points on the circle, and this highlighted part is a portion of the circle contained between those two endpoints. That's what we call the arc. Now, how do we notate this? How do we describe this? Well, I'm going to say this would be arc like that, arc AC. So it's just a little curve like a frowny face or something, upside down smiley face. But that's arc AC. Now, adjacent arcs are arcs that intersect at exactly one endpoint. So let's go ahead and use the radius, because remember the radius, I can move it wherever I want. It's always going to be the same. So I can move this around wherever. And wherever I move this, that's going to create another. So here's a central angle. I get a central angle here. Get another central angle. I also get corresponding arcs here. So there's an arc. There's an arc. Now, adjacent arcs are arcs that only intersect this point D at one point. So arc DC and arc CA are adjacent arcs because they only intersect at point C. Now you cannot have adjacent arcs aren't overlapping arcs. So for example, if I took arc EC, which that's this whole guy, all this right here, arc EC, that would not be adjacent to arc ED because they overlap here. So that's a quick run through of the different parts we're going to be looking at. We have central angles. So if I take my circle, the main thing is I have my central angle here. I have an arc right here. And then adjacent arcs are two arcs that intersect at one point. Now we also have minor arcs and major arcs. Now a minor arc is an arc whose points are on or in the interior of the central angle. So if I look at my central angle right here, so we're looking at this arc, x degrees is the central angle. The minor arc would be the portion of the circle right there that is inside or on the interior of the central angle. Now we only use 2 points to name this. So if you see an arc with 2 points, that's going to be a minor arc. Now to find this, what's easy about this is that if you have the central angle, whatever that is, the arc angle measurement is the same. So the central angle and the arc measurements is the same as they're equal to each other. So right here, the arc measurements and the angle measurement, they're both the same. Remember, there's 360 degrees in a circle, so when we take the arc measurement, we're just taking a portion of that 360. So that's how we measure that. Now a major arc, we're going to use 3 points to name it, and it goes on the exterior of the central angle, or on the outside. You can kind of think the outside of the central angle. So here's my central angle. The major arc is going to go out here. So that's the major arc. Now to find this, if you have the central angle, remember the minor arc is going to be the same measurement as the central angle. So all you have to do to find the major arc is just do 360 minus the central angle or minus the minor arc. And that will give you the measurement of the major arc. And notice that we have 3 points. I'm going from A to D to C. And that describes my major arc here. Now if you have the endpoints of an arc that lie on the diameter, we're going to say that the arc is a semicircle. So here, when we look at this example, the arc starts at point E. If I can get this, point E goes through F to G. Well, here's my diameter. Since it starts and ends on the diameter, we're going to say that it's a semicircle or half a circle, and that's going to be a measurement of 180 degrees. Alright, so let's look at how to solve different questions like this. The last thing we need to know is the arc addition postulate, which states that the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. All this means is that if you take a major arc, that's going to be equal to the sum of the two minor arcs. So if you look at the example here, we're going to say that ABC, this guy right here, that is going to be, or that entire arc is going to be equal to the sum of, just a second, I'm trying to get this to work. It's not working. Okay, so it's going to be equal to the sum of this arc plus this arc, and that will give me the entire arc. So let's go ahead and solve some of these questions. Determine the following. Let's look at the measure of angle BCF. BC Alright, so let's go and look at solving a few of these. Now, the first thing we need to do is note that we're looking at BCF. BCF right here. Will that be BCF? That's obviously incorrect. So go ahead and change this to, let's look at the measure of angle BFC. So sorry about that little mistake. So BFC, that central angle right there, well, that is going to be equal to 50 degrees. Now, why is it 50? Well, notice that I have a semicircle here, that the entire semicircle is 180 degrees. We'll have 90 degrees right here. I have 40 degrees right there. So my unknown would have to be 50 degrees, because 90 plus 40 plus 50 equals 180. Or what we could look at this too is that I have 90 degrees right here, so 40 plus 50 equals 90. Now D, let's look at the measure of angle DFE, so this angle right here. Well, how would I figure that one? Well, notice, hopefully you can spot it, but notice that I have vertical angles here and here. So if this is 40 degrees, then this also has to be 40 degrees, because of vertical angles congruency theorem. Let's look at AFE. AFE. So I know that this is 40 degrees here. I could use vertical angles with this guy and this angle. That'd be fine. Or I know that from A to D is 180 degrees. It's a semicircle. So I could do 180 minus the 40 to get 140 degrees for AFE. Just like that. So I have 140 here. I have 40. Obviously that's 90, and then 50. Now start solving for the arcs here. So looking at this arc here, arc AD, well, I'm going from A to D. It doesn't matter which way I go, because arc AD falls on the diameter, which means it's a semicircle. So since it's a semicircle, the measurement of the arc is 180 degrees. I'll do these in a different color. Let's look at arc BD, going from B to D. Now that's using two letters, so that's going to be a minor arc, which means I have to go this direction, and I want to go the longer direction, longer way. So the minor arc B from B to D, well, that's going to be equal to the sum of 50 and 90. That will give me the central angle right here. So that is going to give me 140 degrees. 90 plus 50 gives me 140, which means that the central angle is 140, which means this arc here is 140 degrees. Let's look at BAD, B to A to D. So that would be a major arc. Well, that's going to be equal to the sum of this angle here, and that angle there. When I add all those up, that'll give me the central angle, and the arc is going to be equal to the central angle, so that gives me 220 degrees. Now let's look at BC, or arc BC, this one right here. Well, the central angle is 50, so the arc is 50 degrees as well. Also a minor arc. DE, that's 40 degrees, because the central angle is 40. And then AE, A to E, well, it's also going to be 140 degrees because the central angle here is 140. So you see the relationship, they're all equal because those are the arcs that correspond to the central angle. Now these down here, obviously you have to use the arc addition postulate, add those central angles, which gives you the arc. Or you can find the arcs and add them together. So not too difficult, pretty straightforward, but just remember that the central angle and the arcs are equal. Now we can also use this example for a little word problem here. So you have a music sales chart, and it's got to be from like the 1980s or something because rock's one of the highest. But notice that we have percentages here. Rock is 25% of the total music sales. So if rock is 25%, and I want to solve for the arc measurement of AB here, well, how would I solve that? Well, remember that our whole circle is 360 degrees. I'm taking 25% of that. So all I have to do is just take 25% or 0.25, because remember 25%, you take these two little dots here, and the way you can think about it is just move them 2 places over. Move the decimal 2 places to the left. That's converting from percentage to a decimal. So you take 25% or 0.25 of the total 360 degrees, and that's going to give you 90 degrees for the rock portion of the sales. BD from here to here. Well, what percentage of the circle is that? Well, it's going to be 13 plus 11, so I get a total of 24%. Well, 24% as a decimal is 0.24. So to do 0.24 times the total of 360 degrees, that gives me 86.4 degrees. So this portion, this arc here, that's 86.4 degrees. Now solve for the arc AC. So A to C. I suggest pausing the video, trying this one on your own. But that portion of the circle is 25% plus 13%. Well, that gives you 38%, which as a decimal is 0.38. 0.38 times the total of 360, because you're taking 38% of 360, that gives you 136.8 degrees. So this arc measurement is 136.8 degrees. Moving on, let's look at our next theorem, and this is using the chords, the arcs, and the central angle. What's the relationship between the chords, the arcs, and the central angles? So remember, here is a central angle. Here's a central angle. If I were to connect the endpoints like that with a chord, and then so I have my central angle, I have my chord right here, and then I also have my arc. So those are the three parts that we're looking at right now. Let me do this. The arc, the chord, and the central angle. So what's the relationship between all three of those? Well, in a circle or congruent circles, if you have congruent central angles, then you have congruent chords. So if my two angles are congruent, so if this central angle is congruent to this central angle, then the chords that are formed are also congruent segments. So that's our first one. So congruent central angles implies congruent chords. That's our first theorem right here. Number one. Congruent central angles implies congruent chords. Well, number two, if I have congruent chords, then I have congruent arcs. So looking at this, let me erase some of this. If I start with my chords here, so if these chords are congruent, then the arcs created by the central angle and the radii, those arcs are also congruent. So our second part is that if you have congruent chords, this implies that you have congruent arcs. And that's our second theorem here. Now our last one, if you have congruent arcs, then you also have congruent central angles. So here, congruent arcs implies congruent central angles. So now I'm going to start with the arcs. So if these two arcs, if they are congruent, then my conclusion is that the central angles are also congruent to each other. So that is theorem, that's this theorem, the three parts to it. The relationship between the central angles, the chords, and the arcs. And if you notice that basically if you have one of these congruent, let's say you have both central angles being congruent in these two parts here, if the central angles are congruent, everything else is also congruent. So if you get one part of those three that are congruent, all three parts are congruent. Here's a quick little proof as to why. If you start with the central angles being congruent, let's say that's our given information, then we know that these sides are all congruent because they're all radii. You take the radius, move it around, and since all radii are in the circle are congruent, the sides which create triangles are also congruent, which means our triangles are congruent by side angle side, therefore everything is congruent by CPCTC. Now how do we use this? Let's say in our first example, we're given the information that QR is congruent to ST. So my chords are congruent. Let's find the measurement of arc RQ. So I'm looking at this arc here. So how do I find the measurement of arc RQ? Well, since my chords are congruent, these two arcs are also congruent. Here's the given information for the arcs. So I can do 3x plus 22 equals 4x, and then solve for x. So x is equal to 22, and then I can plug it back in to solve for the actual angle, the arc measurement. So the measure of arc RQ is equal to, it doesn't matter which one I plug it into because they're both congruent. So I get 88 degrees for the arc. Example 4, I'm given the central angles are congruent. Measure of angle HLG and KLJ are congruent. So let's find the arc measurements. Now, in our next example here, we're given the central angles as congruent, and let's go and change this. That should be segment GH. We want to solve for the chord here. That's the information that we want to solve for. Let's solve for GH, segment GH. Now, since these central angles are congruent, the chords are also congruent, so I do 2y plus 5. I can just set them equal to each other because they are congruent. Y plus 13. which gives me y is equal to 8, which when I plug it back in, it doesn't matter which of these I plug it back into because they're congruent. I plug it back in and I get 21. 16 plus 5. Alright, so that's how you solve using these relationships between the chords, arcs, and central angles. Alright, last theorem for today. In a circle, if the radius or diameter, either one works, if the radius or diameter is perpendicular to a chord, then it bisects the chord and the arc. So if I take the radius of a circle, let's say that I construct an arc, no matter where I move, so alright, so our last theorem for today, theorem 12.2.3. If you have a circle and if the radius or diameter, either one works, if it is perpendicular to a chord, then bisects the chord and the arc. So if I take the radius of a circle, and if it is perpendicular to any given chord, it could be that one, it could be this one, it just has to be that one, it just has to be perpendicular to it. If it is perpendicular to that chord, then it bisects the chord and it bisects the arc. But it has to be perpendicular to it. That's what our first theorem here states. So if it's perpendicular, conclusion, it bisects the chord and the arc. Now conversely, if you have a circle and the perpendicular bisector of a chord is if you have the perpendicular bisector of a chord, then that perpendicular bisector is the radius or the diameter. So on this one, I'm going to start with a chord and a segment that bisects the chord or the arc. So if we start with that information, my conclusion is that the segment that bisects the chord or the arc, that this segment here, geez, I can't do it, that segment, that's going to be either the radius or the diameter, because for all we know it could go to the other side. So that's the converse. We start with a perpendicular bisector, and yes, it does have to be perpendicular, so you can't have something like this, right? It has to be perpendicular. Then if you have that perpendicular bisector of the chord, then it is the radius or diameter of the circle. Alright, so how do we use this to solve different questions? Alright, so our next example, our next theorem, which is the converse of our first one, this starts with a perpendicular bisector of a chord. So if you have a chord and you have a segment that is perpendicular to the chord and it bisects the chord, my conclusion is that that segment that does the bisecting of the chord and is perpendicular to it, it's either the radius or the diameter. Because for all I know, this segment could keep going to the other side of the circle, so it's going to be either the radius or the diameter. So you start with a perpendicular bisector of a chord. My conclusion is that it's either the radius or diameter. So it could be the radius as well. Now how do I use that to solve for different questions? Well, this one, our first example, we're supposed to solve for NP. So I want to solve for this segment right here. So how do I solve for that segment? Well, let's first see what we have. I'm going to start with a segment that is perpendicular to this chord. And note, that's also the radius because it starts at the center and goes to the side. So I have a radius that is perpendicular to a chord, which means it's also bisected. Well, how does that help me to solve for NP when I don't know what this length is here? Well, what we can do, this is kind of interesting, is that I take the radius. Remember, no matter where I move the radius, it's always going to be the same. So I'm going to move it up here. What's the length of the radius? The length is 10. So what I get is actually a right triangle with the base being 6. This side is unknown. I don't know what this side is, and the hypotenuse is 10. So I can use the Pythagorean theorem to solve for my unknown side length here. And what I get when I solve is, it's a 345 times 2, so x is equal to 8. So this side length here is 8. Now it's bisected, so I double it to get the full length of NP, which gives me 16. Same thing with example 6, same concept. I have the radius, it's perpendicular, so it bisects it. I create my right triangle here, which the radius is 17. So I will get, if I set up my right triangle here, hypotenuse is 17, this base is 8, unknown there. So 8 squared plus x squared is equal to 17 squared. I get x is equal to 15. So I'm solving for EF, which is the entire chord here. It's bisected, so I multiply that by 2, and I get EF is equal to 30. Yeah, so obviously you could use the converse. If you start with something that's bisected, you know that the segment that's bisecting the perpendicular bisector is the radius or diameter. So yeah, that's all for the lecture today. Email me if you guys have questions. Make sure you guys do the homework, and have a good day.